4 times 10 to the 4th power.
One, two, three, four. Bingo. Everybody get that? We got questions if you didn't get that. Pretty easy, right? Let's try a small one. Let's try a small number. So we've got 0.0000927 liters. I want you to put this number into scientific notation. We got an answer yet?
I think I do. 9.27 times 10 to the negative 5th power. -5.
Anybody else confirm that our exponent is -5? Yeah, I see some shaking heads. Good. So let's double check. We know our numbers over here. We've got to turn these important numbers in between 1 and less than 9 or less than 10. So my decimal point's got to go there. So let's see how many places I got to move it. 1, 2, 3, 4, 5. I know it really is not 5, so I'm moving it over here to my right. So my base here is bigger than what my number really is. So I've got to do something to make this base smaller. I've got to multiply it by a small number, or I know I'm moving my decimal point to the right. There we go. I'm moving my decimal point to the right, so I know that my exponent's got to be negative, right? So 9.27 times 10 to the negative 5th. Good work. Now, I want to do an example of taking a number from scientific notation and writing that number out. So let's do well, not seconds. That's too tiny for a second. Let's do a gram, and then let's do this one a kilogram. Okay, so we've got two numbers up here. I want you to write these numbers out in what we call expanded form, or that whole big giant real number. You guys done writing zeros yet? Hopefully you can see as you're writing out all these zeros and double counting them, that scientific notation is a way more efficient way to deal with really big and really small numbers. Okay, so if we are taking this first one, 3.4 times 10 to the negative 13, is this, just looking at this, is this number really big or is this number really tiny?
Really tiny.
Really tiny. How do I know that?
Because it's negative.
Yeah, so negative exponents always mean really tiny numbers, just like positive exponents mean really big numbers, right? So that's a clue that will help us to interpret those numbers and make a little bit of math sense for us so that we can kind of double check ourselves or understand a little bit more about those measurements. So negative exponents, so my number is going to start out over here, and I've got to move this decimal point. This is going to be my final answer. I've got to move it 13 places that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I can't leave off any number from here. So I've got to double check and make sure. Now let's count and double check ourselves because I might have left off a 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Bingo. So you should have 12 zeros. And then we can't leave off our units, gram. So bonus question. What kind of value was this measurement of? What did it measure? I see a G right here. Did it measure a volume? Did it measure time? What did it measure?
Mass.
Mass, right? So this is mass. Good. Same for this one. It's just a kilogram. This is just a different mass unit. So let's look at this one. This one is a positive number. So this is going to be a big number. We're going to move our decimal point the opposite of what we did for our negative exponent, for our small measurement. So this one, we move our decimal point 9 places this way, right? 9 places to the right. So 1, 2, 3, 4, and the rest are going to be zeros. 4, 7, 3, 0, 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And I fill in with zeros. And I double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Erase all that. And I've got kilograms. Okay. So, hopefully you guys solved these pretty easily. Do we have any questions? Please don't be ashamed to ask questions. That's okay. If you have that question, somebody else probably does too. Cool. We'll be working in chemistry, particularly with really small masses and really big numbers of things. Because we're learning about atoms and molecules in this class, right? Atoms and molecules are really tiny. So we'll use scientific notation a whole bunch, especially in big giant fractions. So it's important, and I'll give this plug now, that you guys have a calculator, even if it's on your phone, that you understand how to use. We'll take some time here in a couple of labs classes where you guys can bring in whatever calculator you use, and we'll make sure that everybody understands how to use their calculator the right way. Because calculators only do the work that we program them to do. If we program the work incorrectly, they're going to do what we tell it to do, and that might be wrong and give us a wrong answer. So make sure you've got a calculator that you understand how to use that will do exponents and divide with those exponents. Okay. Now, scientific notation. Do you guys need to see extra unit conversion practice problems? We feel good with unit conversions. Okay. Hopefully the work we did last class really helped that, and we understand how to do that now, because that is a core component of chapter 1. You can expect to see several of those kinds of questions on your test and in the topics coming up in the next few chapters. Unit conversions won't go away, so hopefully you know how to do this. Okay. Last chance. Any questions on unit conversions? Cool. Okay, we're going to move on to density. So I sent you guys a link to the activity that we're going to do in class together. So I'm going to show it on our screen. And if you have it, you can pull it up on your computer too. Not that one. This one. Cool. So our last topic for this chapter is density. So we have an activity that is going to teach us what density is and how to calculate that density. So am I sharing my screen with you guys, or do y'all see me? Yeah.
I just see you.
You just see me. Okay. Then I'm not sharing my screen right. I'm learning all this stuff too. Now, can you see my screen? Or do you just see me?
I see your screen now.
Okay, great. Perfect. That's what we need. So here is our activity. So our question that we're exploring with this is called, what is density? So we've heard about density before. If you've taken a science class before, even elementary, you've probably done the little classic experiment where you make stuff float on the water and some of the stuff sinks in the water, right? So we can take a piece of tinfoil and we can make it into a boat and make it float, but we can wad that same size piece of tinfoil up and put it in the water and it sinks. So this activity is going to help us understand the science behind that. So we see in our model, we are comparing two values. So anytime you see a graph, one of the first things that you have to do to understand that graph is look at what your axes are measuring, right? So down here on the bottom, this is our x-axis, and we see that it is labeled volume. And that volume was measured in milliliters. So this parentheses right here tells us what that quantity was measured in. And then if we look on our y-axis right here, we see that these values are mass values, and they were measured in grams, right? So anytime we see a point on our graph, we know that this point gives us an x value if we follow it down onto our x-axis. And if we follow it over here to our y-axis, it gives us a y value or a mass value, right? So this is just like a coordinate system in your math class where you've got a x comma y and you graph it and make a line. That's a whole bunch of algebra, right? So here we're applying that algebra and looking at how we understand how these measured values relate to each other. That's all a graph does. It shows us how two different pieces of information relate to each other. We see in this graph, we see some nice little straight lines. So we have some linear relationships, and we'll talk about a little bit more about that in a little while. So we've got some volume and we've got some mass and we've got some pictures. We've got 4 different substances, A1, A2, B1, and B2. We see all these little dots in here inside each cube. Some have a bunch of dots, some have just a few dots. So let's see. How many dots are in each of the cubes? So in A1, count those. Let's see how many dots there are. Once you count in A1, I want you to count A2. Okay, we got some dots. How many dots are in A1?
16.
16.
So an easy way to do this, since we know it's a cube, count across, count down, and multiply. So 16 in A2, how many did you guys get?
64.
Mhm.
Yeah, good. It's 8 by 8. Okay. In B1, how many did we get? 4. Hopefully you got 4. And in B2, we got
16.
16. Okay, good. So just looking at these, what's our biggest difference between our cubes? How are they different?
The B1 and B2, the dots are more spaced out.
Yeah, so they're, even though like B1 and A1 are the same size, right? They take up the same amount of volume, right? So if we look right here, they both have the same volume measurement, right? So if I'm looking here at how my bottom is graduated, right? Each little line represents 1 milliliter. So here, my A1 and my B1 both line up at this point. So if I count over, that's 1, 2, 3. So 5, 6, 7, 8. They both take up 8 milliliters of space. That is their volume. The same for my A2 and my B2. They both line up on the same point for my volume. That would be 32. Okay, but B2 has way less dots in it than A2. So based on what we just looked at model 1, what corresponds to our mass? What's going to be the direct part about each of these pictures that relates to mass? And to help you answer that question, let's examine A1 and B1. So B1 right here had 4 dots, and A1 had 16. So let's look at their mass. So to find their masses, where do I get that information from my graph? Where do I have to look?
On the, was it the y-axis?
Yes, it's the y-axis. So that information for mass is given to me in my graph because that's what my graph is measuring on this y-axis. So if I look over here, I see the mass for A1, if I follow this line over, is, okay. Oh, here's another important thing to consider. Do each of these markings represent 1, or do they represent something different on my y-axis? Down here on my x-axis, each line represented 1. There were, between 15 and 20, there were 4 little lines. Is that the same on my y-axis? Is it graduated the same?
No.
No. So what does each line represent?
Two.
2, right? So each one represents 2. So this line would be 12, this line would be 14, 16, 18, 20. So A1 right here lines up here, and that is 12, 14, 16. So A1 had 16 dots and had a mass of 16 grams. B1 had 4 dots, and what is its mass? You look on the graph, where does it line up?
4.
4. So what does each dot represent? What you guys think?
Their mass?
Their mass, right? So more dots, more mass, less dots, less mass. Let's double check our hypothesis. Let's examine A2 and B2. Before we measure them though, if we're right, A2 had a mass, had 64 dots. So if we're right on our y-axis, it should hit over here at 64, 2, 4. So that would be at this point on our graph. So if I follow it over, is that where it hit? Bingo. So we're right. Each dot represents 1 gram of mass. So B2, less dots, way less mass, even though it has the same size as A2. We see that same relationship here with A1 and B1. They have the same volume, so they take up the same amount of space, but A1 has way more dots, so its mass is greater than B1. Okay, so we've answered question 3. Okay. So let's answer question 4. As volume increases on the graph's x-axis, what changes about each cube? So looking here, as we track along our x-axis, so as we move from left to right, as we read our x-axis down here, our lines go up. So what is different about A1 and A2? How do they relate to each other? Is there a pattern in how A1 and A2 are related and how B1 and B2 are related?
The lines they're graphed on.
Okay. So there's obviously some pattern there, right? So what is the same or different about how the dots in B1 are organized and how the dots in B2 are organized? Is there the same amount of space in between the dots in B1 and B2?
Yes.
What about A1 and A2? Are they organized inside the same?
Yeah.
Yes, right? And we see that their mass and their volume follow the similar pattern because they have this perfect straight line. If this was not a straight line, there would not be a direct relationship between A1 and A2, right? So this straight line right here between those 2 points is just telling us that A2 is like twice as big as A1, right? So we could guess, right, at any other point on this line that our cube A, another iteration of it, could be A3, would look very similar on the inside as A1 and A2 because there is this direct relationship. So anytime we have a straight line and we have points on that straight line, those points are all related, right? If you've taken that far in algebra, you know that as slope, right? So any point on this line has the same slope, or any 2 points, there's the same slope there. So that shows that there's a relationship. For this one, it is a direct relationship. As one of our values increases, the other value increases by the same amount, right? So if I were to extend this line, right, I know that if I picked a 0.35 volume, I could see where that would hit this line and I could know what mass we would expect a similar shape or similar object to have. The same for down here. I could guess at a volume of 20 milliliters what mass would correspond to this same item. So if I wanted to know at 20 milliliters what mass a cube of type A would have, all I would need to do was go to 20 milliliters and go up on this graph and find where it hit. So if cube A had a mass of 20 milliliters or a volume of 20 milliliters, I would expect that cube to weigh 40 grams. You guys see that? So this is how we can kind of use a graph to show relationships between values. So let me ask you this question. A 20 milliliter sample of cube B, what would we expect that to weigh according to the information in our graph?
10.
10, right? Because that's where it hits. Okay. So we could use this data to do what we call extrapolate. So that means we could make our graph bigger. So I could, like, in my head, expand this graph and the line's going to be a straight line. So I could figure out a ton of different information if I needed to. We don't need to for this one. But that's just to show you what can be done on graphs like this, because we'll start to see graphs like this a whole lot more, even inside your readings. Okay. So cool. So let's look here and let's try to fill in some volumes. So we want to use the data to find the volume for our cubes. So we're looking at, once again, these two objects, objects A and object B, and two different samples of those objects. So we want to figure out the volume for them. So how could we do that? We could look at our little cube here, and to get a volume, we have to know a length, we have to know a width, and we have to know a height, right? Volumes are this cubic measurement. And you have some information down here for that. So we have a length, we have a width, and we have a height. So we have to multiply all of these units together to give us our volume for that object. While you guys do that, I want to know what unit all of our volumes will be in. So before you even do any calculations, what is the unit going to be for our volume for all of these cubes?
Centimeters.
Is it just centimeters?
Cubic.
Cubic centimeters. So that would be a centimeter with a little tiny 3, right? Because we're literally multiplying 2 centimeters by 2 centimeters by 2 centimeters. So that's going to give us 2 times 2 times 2, which is 8, right? 4 times 2, yeah. But then when I multiply centimeter by centimeter by centimeter, I still have 3 centimeters. There's nothing's canceled them out. It's not like a unit conversion. They're still there. So our volume for this first one is going to be 8 centimeters cubed. What were our volume for A2 be?
$31.167.
Uh-oh. I got something different. Hold on, let me put it back in my calculator. So 3.174 times 3.174 times 3.174. Yep, I got what you did. So that would be 31.98 centimeters cubed. So why did I round? And this is, let's just do all the other ones and then we'll talk about sig figs, because I'm going to show you guys this chart. So B1, what'd you guys get for B1? 2 times 2 times 2. It's the same as A1, right? B2. Oh, hey, it's the same. Doesn't that make sense? Because if we look at our graph up here, they have the same volume. So even though we're calculating its volume in a different unit, if our chart is to be trusted over here, they should have the same volume regardless of what unit we measure it in. And we see that over here looking at their actual measurements. So looking at our little chart here, I know that glare is bad. I'm working on some better lighting. If I move it, it's just going to move it. Anyway, so why did I round to 31.98? Because if you did that in your calculator, it gave you a whole big long number. Why did I choose to round it here?
Because the base number was only 3 places after the decimal point.
But this place is not 3 places after the decimal point. How many significant digits did my base numbers have for A2 and B2? That's 4, right? So my answer has to be rounded to 4 significant digits if I'm going to conserve the accuracy of that answer, because I'm multiplying. So I have to go by sig figs and not decimal places. Here, all my numbers were rounded to the nearest whole number. So I had, can only have 1 significant digit. So we didn't have to do anything crazy with those. Okay, so this is an example of how we kind of apply those rules for accuracy and precision into our derived values, because these are derived measurements. We took 3 separate measurements and we did something with them to calculate this new kind of super measurement, if you will, or this measuring in 3 dimensions. Okay, so let's move on and let's look at some of our other ones, because you guys are getting bored. I can see it in your faces. Okay. We've talked about all those. So now let's kind of do some summarizing. Looking here, our density is going to be our measurement for how our mass and our volume relate. So density is basically this line right here. So density, if we look at our measurement for density, according to this graph, would be a gram per milliliter. So a gram over a milliliter. So we're looking at our ratio of mass and volume. So if we look at A1 and A2, they have, even though they're different, A2 is a bigger piece of, it's bigger than A1, it still has that same relationship between its mass and its volume. All right, and we're going to see that when we look at here and do some calculations. So let's look at this one. So we've got these right here. Which one would you consider more dense? Would it be this first one, or would it be this second one? Which one has a bigger, if you will, ratio of its mass to its space?
The first one.
Why would you say it's more dense?
There's more objects in it.
Yeah, there's more stuff in it, right? And if we remember, each of these dots represents 1 unit of mass. So this has more stuff crammed in the same amount of space, right? So it's more dense. Think about it. I like to go to amusement parks. That's kind of my family's thing. And I would way rather go to an amusement park when it's like this cube over here than when it's like this first cube right here. This one has way more people. The lines are going to be way longer, right? We're not going to get to do as much. It's just thicker. This one over here would be like a good day to go to an amusement park because there's not as many people. You get to do more stuff. It's a lighter and a more fun time. Okay. So looking at our picture, we put an extra line here in the middle, and this represents the density of water. So we could draw little boxes here that would show the relationship between the mass and the space of water. But we can also use this density to help us do something really practical for our study of chemistry and for your study of physics if you go on to take physics. Things that are more dense sink. Things that are less dense float. Right? So here's our line that represents the density of water. What is going to happen to anything that is above this line? So like our cube A. Do you think its density is going to be heavier than water? Or you think its density is going to make it lighter than water and make it float? What you think?
Heavier than water, and it'll sink.
It will sink. So for something to float, it has to be less dense than what it's being put into. For something to sink, it has to be more dense than what it's put into. So water is right here. Our object A is above that. It has a greater mass to volume ratio than the substance it's got to push out of the way to float. So object A would definitely sink. Object B down here has more space between its particles, right? So it weighs less, even though it takes up the same amount of space as water. So it can't push the water out of the way for it to sink. So object B down here would most definitely float on water. What would happen if I put a substance that had the same density as water into water? Would it sink or would it float? What you think?
I'm trying to think of like oil in a way, so I guess it would sink because when you, or would it kind of like float, kind of make layers?
It would kind of like suspend in the middle
Yeah.
of the water.
Yeah, it
Right?
would make a layer. Yeah.
Yeah, it would kind of make a layer, yes. So we can use this kind of, if it floats or if it sinks, as a way to qualitatively measure density. So we can measure density without even having to do any math. It's not as specific as if we did the mass and volume ratio, but we can use it and physically like guess what its density is compared to what it's floating in. So if it has a very similar density, it's going to like suspend in the liquid. If it's got a much bigger density, it will sink and it will sink quick. And if it's got a very small density compared to what it's in, it's going to float directly on the top. So I think about fishing, right? So you've got the cork. It has a really tiny density because it's got to float on top of the water. And then we've got the bait and the sink that's going to help our fishing line go all the way down to the bottom where the fish are. It's got a big, heavy density. It's real thick. It weighs a lot for the space that it takes up, to kind of help you understand that. So let's take a minute and let's look at question 3. And then we'll do some actual math and quantitatively calculate density. Oil floats on top of water. We want to try to draw a picture using our dots like our model to show what our oil is going to look like. Is it going to be more like object B or is it going to be more like object A? So I know you guys got some scratch paper around, so draw a little box to represent some oil and try to space out some dots in there or condense some dots in there based on what you think. And I'll show you my picture. Looking at this problem, what is the important information for us? What is our number one clue that lets us know what kind of dots we need to draw? If I were circling important information for question 3, what word would I circle?
The fact that the oil floats
Yes,
on the
the
water.
fact that the oil floats. That is going to tell me what about its density? Is it very dense or is it not dense?
It's not dense.
It's not dense. So if it's not dense, there is a lot of space in between the little dots, in between its particles, right? So I should draw a picture that is more like this, right? Our object up here on the right than our object on the left. Right? And I'll show you guys my little picture. Yeah, so here's my little picture. I got 4 dots like a dice, right? So oil is really light. It has a very low mass to volume ratio. It doesn't weigh a lot, but it takes up a lot of space. So now, how do we actually quantitatively calculate density? Because that's the last math part for here. So we see over here, our density is a gram per a milliliter. So when we see this slash right here, that should clue us in mathematically to how they calculated this number over here. What did they do with their mass and their volume to get this density? How do they manipulate these numbers to come up with a unit that has a gram on the top and a milliliter on the bottom?
They divided it.
Yes, they divided it. So density is our mass divided by our volume. So if you ever forget and you don't know that, or it's hard for you to remember that, look at your unit for density and that will tell you mathematically what you need to do with those numbers. So to calculate a density, you have to divide a mass by a volume. So I think in your book, it gives you that formula. D is equal to M over V. Density is equal to mass divided by volume. So looking at our calculated density here for objects C and D, right? So object C had 8 grams and 5.33 milliliters. It had a 1.5 grams per milliliter density, the same for object D. So do you think these have the same relationship to each other as our object A1 and A2 had, and our object B1 and B2? Do you think object C and D are made out of the same thing? That's another way to phrase what I just said. So looking up here, object A1 and A2 were made out of the same material. Object B1 and B2 were made out of the same material. So do we think that these two objects are made out of the same material? If we were to put these two objects on our graph with A and B objects, would they make a straight line like our other two sets? What do you think?
Yes.
Yes, absolutely. Right? So these both have a linear relationship between their mass and volume. So their density is exactly the same, right? That means how these two variables relate to each other yields this same ratio. So they have the same density. They are most likely the same object. Okay, so we want to calculate and confirm this, right, with our first two objects. So we have already calculated the mass and volume for each of these, right? So we're going to look at the density now. So we'll do the first object together. So the mass of this object, object A1, was how many dots it had? So how many dots did A1 have? It was 16, right? What was its volume? If we go back and look, we've calculated it, but we can just look on here. It was 8, right? So what is the volume, or what is the density of object A1? 16 was its mass, and 8 was its volume. What's its density?
2 grams per milliliter.
Bingo! Be more confident. 2 grams per milliliter, right? So does anybody off the top of your head know what the density of water is? No, some people do. It's 1, right? So water is our kind of standard for all these density values, and its density is pretty close to 1. So this object right here, if we put it in water, it has a density that's higher than water, so it's going to sink, just like we saw when we added the line for water. Okay, what would we expect our density of this A2 up here to be? Do we think it's going to be 2? Or do we think it's going to be different? Hopefully you're thinking it's going to be the same. So it had a volume of, see, we calculated out. We're just going to use it rounded on this one. So about 32. All right. So for A2, it had a volume of 32 and it had a mass of 64. We'll go ahead and get information for B1 and B2, and then we'll do the math together and I'll show you on my whiteboard. So B1 also had a volume of 8, and B2 had a volume of 32. And then our B1 had 4 grams and our B2 had 16. Okay, so looking here, we've got 64 for our mass and 32 for our volume. So 64 divided by, I'm going to just draw a line here to show us that that's what we're doing, because density is equal to mass divided by volume, right? So mass divided by volume. For A2, you should have gotten a density of 2 grams per milliliter. And for B1, you should have gotten 4 divided by 8, which gives us what? A half, right? 0.5. And then B2, 16 divided by 32, but look at there. 16 is half of 32, so it should also be 0.5 grams per milliliter. Are there questions about how to calculate a density, or what it means when something is dense, less dense, and how we can predict if something will float or not? Because those are your main skills for density and our practical purposes. There's one way we could take this deeper, right? But I want to make sure before I show you an example of that, we don't have any questions about how we calculate a density. If I give you a mass and I give you a volume, or if I give you the tools to measure mass and measure volume, can you calculate a density? Now's your time to ask questions if you're still unsure about mathematically how to do that. We good? Give me a thumbs up if we're good. Great. Okay. Now, the only other way that we could ask you about density, mass, or volume is if I gave you a density let's say something was 2 grams per milliliter. And I told you that you had 24 milliliters. And I wanted to know how much that would weigh. So let's say we have a substance that has a density of 2 grams per milliliter, and I hand you a beaker that has 24 milliliters of that, and I wanted to know exactly how much that would weigh. How could I use this information and my relationship that I know exists between mass and density and volume? How could I solve for my mass? Right? So this is now it basically just becomes an algebra problem. Density is this. So 2 has to equal my unknown mass divided by my volume, 24 milliliters. So how do I use algebra to help me rearrange that and figure out what M equals? In math, how do we undo this and get M all by itself?
Multiply.
Yeah, so I do the opposite, right? So here I'm dividing by 24. So if I want the 24 to go away, I've got to multiply it by 24. Both sides by 24 milliliters. And oh, look, I do that because I want the unit and the number to cancel out and to go poof from this side of my equation. We just saw that when we did unit conversions too, right? For something to go away and disappear, it's got to show up on the top and the bottom of my expression. So I multiply here. Both of those go away, and I'm left with 24 milliliters times 2 grams per milliliter. So I've got a milliliter on the top and a milliliter on the bottom. So my milliliters disappear, and I'm left with 24 times 2. So the mass of this object at 24 milliliters has to be 48. And what is the only unit that's left over for that? Once I do the smush this over here, it's a gram, right? So you can use your units as a guide if you do problems where you have to figure out mass or volume. If when you do your math, all your units except the one for mass don't cancel out, you know, you did something wrong if you're looking for a mass, right? So you get your units can be your guide. Okay. So hopefully. So we could have done the same thing with our volume, right? We would have just had an unknown on the bottom. So we would have had to do a little bit of different algebra to get that one on the bottom by itself. Okay. So hopefully the math today wasn't too bad for you guys. We just kind of recap, we did scientific notation. We looked at conceptually what density is and how we can predict if stuff is going to float or sink. And then we looked at how we quantitatively calculate density using the relationship between mass and volume, and how we could even figure out a mass or a volume if we know the density of a substance. Okay, so questions about density before we kind of end class today? Hopefully looking at the pictures helped you get a good visual of what density is. So from here on out, when we talk about density, you can kind of understand that it's a relationship between the space something takes up and how much it weighs or how much is in it. Other than that, that's the last big topic in chapter 1. So you guys can give yourself a pat on the back. You've survived the beginning of your chemistry study. For tomorrow, today and tomorrow, you just need to make sure that you read the density stuff in our textbook. My face. And kind of cover up that. Finish your glossary. So any of the vocabulary words that you haven't had a chance to add, go ahead and spend some time studying them by adding them to the glossary. And then you're also going to have posted tomorrow our last summary activity for this unit, and it's going to be called a one-pager. So basically, you are going to take all the topics you've learned about in this chapter, and you're going to give me a kind of visual representation of that. There'll be a rubric for you and more specific instructions, but it's a way for you to be creative and kind of process the connections between all the topics that we've experienced in this chapter. So if you're creative, you should really like it. If you're not creative, you might not like the activity, but it's to show you guys different ways that you can process your own learning. We all have different ways that we learn, and this is just to kind of show you guys another way that you can process lots of information, just another way. Kind of like our glossary is a way to do that as well. So tomorrow's activity will also include the chapter review questions. I will post an answer key for that for you to check your work tomorrow after you've had a chance to work through all the questions. If you can answer all the questions in the review and get them right, you're going to make at least an A, maybe even 100 on our test on Friday. So that's how you'll know you're prepared for the test. You can also look back through all the objectives that I had on our weekly instruction sheets or your assignments. If you can do all those objectives and read all those statements and they be true for you, you're going to do well on the test as well. So yeah, hopefully chapter 1's our entry one. You guys have done really well in the lab, so I feel like y'all's math skills are advancing right on where they need to be. So any last questions for me before we end today and you guys get to it? Okie dokie. Well, thanks for hanging in there today. I will post a recording of this if you want to go back and look through it a little more. It'll be there for you probably this afternoon. So if not, I'll see you guys on Thursday. Bye.